Hello everybody, welcome to another video lesson. We are wrapping up our chapter on sequences and series by looking at functions as infinite series. We're going to use power series to represent sine and cosine functions and even getting into complex numbers. So let's take a look at our power series representations for sine and cosine. Now we did a lot of deriving equations and deriving representations last lesson, so I'm not going to derive these two. However, we do need to have these written down and understand the pattern that we are seeing when I represent cosine and sine as infinite series. So go ahead and write these down. Let's also take a look at Euler's formula. This is going to help us represent complex numbers in exponential form. Okay, so we'll start off here with our Euler's relationship, our Euler's formula. And we're going to substitute now, instead of x, I'm going to substitute in I theta. So when I do that, I get something that looks like this. And really this is a representation, or this is the expanded series of the sum from n equals 0 to infinity of I theta raised to the n over n factorial. Okay, so I've just expanded this out. Now if I expand this out even more and kind of start to simplify, we start to see some patterns. Because every time I have I squared, that gives me a -1, right? So you start to see this pattern coming up where I have a real component or a real term and then an imaginary term. And then they come in pairs, so I've got real and imaginary, and those are both positive. And then two terms that are going to be negative, one real, one imaginary. And then two terms that are positive again, one real, one imaginary, and it just keeps on going. Now, we need to start pairing these off, and we need to start grouping these because we're going to see, again, a pattern that will refer back to what we just looked at last slide with our sine and cosine representations. So I'm going to go ahead and group all of the terms that are real, and then I'll separately group all of the terms that have an imaginary component. So when I do this, I get 1 minus negative theta squared over 2 factorial plus theta to the 4th over 4 factorial, and you just keep going with this pattern. And then all of my imaginary terms have this similar pattern as well. And if you go back to the formulas from last slide, you'll see that what I have in this first grouping is actually the series representation for cosine theta. And over here, if I were to factor an I out, because all these terms have an imaginary component I, then what I'm left with in this parentheses is actually the series representation for sine theta. Okay, so really what I have is my Euler's formula for any real theta value. E raised to the I theta is equal to cosine theta plus I sine theta. Now, recall, this should look familiar from our last chapter. Doesn't this look like part of the polar form of a complex number? It does, right? Now, only thing we're missing is going to be our R value. Okay, we just need our R value. So if I were to just plug this into here, then what I'm left with is going to be R e to the I theta. So with this, we can now express complex numbers in the exponential form, something that we haven't been able to do previously. So I can represent A plus BI in exponential form as R e to the I theta, where R is still the square root of A squared plus B squared, and we find theta with our inverse tangent relationships, just like we did in our polar unit. All right, let's get into some examples here. First off, using the sine function, we're going to use the fifth partial sum of the power series for sine to approximate sine of pi over 11. So looking at our power series for sine of x, now anytime I see x within this, x is equal to pi over 11 in this case. Okay, so the fifth partial sum here would be the sum from n equals 0 to 4, which is going to still give me this here equation, or this representation. So in this representation, everywhere I see x, I'm just going to plug in pi over 11. And from here, don't try to simplify this any more than you have. Okay. Now notice, again, I've got the fifth partial sum, which means I end here on n equals 4. Why is that? Because we started at 0, so I have 1, 2, 3, 4, and 5 terms right here. Okay, so we don't need to go any further than that. Now, in my calculator, this is how I plug this in. Now notice, this does not matter if I'm in radian mode or degree mode, okay? So when I do this, I'm going to get 0.282 rounded. However, what does matter is if you were to check this using your calculator, which you should do because it's very simple. All you need to do is input sine of pi over 11 into your calculator, except make sure you are in radian mode. Okay, make sure you are in radian mode for when you do this check. Again, over here doesn't matter when I'm doing my series representation, but if I were to just plug this in, this needs to be in radian mode. And again, I get an approximation of 0.281 and a bunch more decimals, so I can see that my approximation is good because those are very, very close figures. All right, taking a look at complex numbers now, we're going to write 1 plus square root of 3i in exponential form. So I need to think of this in polar form first, where a is 1, b is the square root of 3, and a is going to be greater than 0. It's a positive value. So r I find just the same. I take the square root of a squared plus b squared. That's going to give me 2. And then finding theta next, we would do that with the inverse tangent of 1 over square root of 3. And you could rationalize that to be square root of 3 over 3. And that gives you a theta value of pi over 3. Now you need to be comfortable with your unit circle in order to figure that part out. But we've done that in the past, so I won't go into it. But now we can represent a plus bi, which is what we have right up here, a plus bi. We can represent that as r e to the I theta. And we know r is 2, we know what theta is, so we have our exponential form. All right, last example here, we're getting into natural logs and logarithms. Okay, we're going to find the value of the natural log of -8 in the complex number system. Now recall, natural log and logarithms of negative numbers, those don't exist, right? That's a domain restriction for us. Now, in fact, they don't exist in the real number plane. However, in the imaginary plane, they do exist. And we're going to use our Euler's formula in order to figure this out. So e raised to the I theta, again, that's cosine theta plus I sine theta. I'm going to set theta equal to pi. Okay? When I set theta equal to pi, I get this formula here. So e to the I theta, cosine of pi, sorry, e to the I pi. Cosine of pi is -1, sine of pi is 0, so this term goes away. So e to the I pi gives me -1. Now, if I were to solve this for I pi, I would take the natural log of both sides, and I find that the natural log of -1 is equal to I pi. So we do actually have a number here for the natural log of a negative number, in fact, -1. It just exists in our complex plane. And the natural log of -1 is, in fact, I pi. Now, that's -1, but we can also take a look at the natural log of any negative value. Okay, so natural log of -k, I'm going to think of that as the natural log of -1 times k. Now, we can use our product property for logarithms and expand this into the natural log of -1 plus the natural log of k. We just found the value for this, so that's going to be I pi plus natural log of k. And if I write this in the form a plus bi, that's going to be equal to natural log of k plus I theta. So a lot of setup there for this problem, but it's pretty easy once we actually find the value of natural log of -8. Okay, so we're going to think about natural log of -8 as natural log of -1 times 8, and natural log of 8 plus I pi, and you can plug this straight into your calculator, and that gives you an estimation of 2.08 plus I pi. All right, guys, that is it for this lesson, and that is it for Chapter 10. Good luck with your practice.